Kind of got rushed yesterday. I want to finish the point I was making yesterday. Okay, so I am recording. Thank you. So what about a problem like this, where we're using these binomial factoring patterns? There's a couple ways you can approach this, but one way is definitely better. So we could, this problem, we could divide both sides by 2. We could factor out an x, which gets us to there, right? And then we could do this one of 2 ways. So one way we could do this is we could look at this binomial factor in here, and we could think of this as a difference of cubes, right? One we could think of as being either 1 squared or 1 cubed. That's not a problem. But 64x to the 6th, we could think of that as being 4x squared quantity cubed, right? Or how could we think of that as being something squared? What would the packets that are being squared be?
8x cubed.
8x cubed. Okay, so we could also write it this way. Right? We could also write this as x times 8x cubed squared minus 1 squared. Either way, right? Both of those should work, and they do, but one of them is just a lot easier than the other. Let's kind of think about why this might be the case. So we started to go through this process, right? We're just following the pattern here. If we have a difference of cubes, just remind me what that pattern is. A cubed minus b cubed factors to a minus b times
A squared plus b plus c.
There you go. Okay, so then that's our a, isn't it? 4x squared, and that's our b, 1. So we get a minus b times a squared. Well, 4x squared, quantity squared, would be 16x to the 4th, plus 4x squared times 1 is 4x squared, plus 1 squared is 1, right? Okay, not bad. But then here's where the problem is. What am I going to do with that? I get two zeros pretty easily, right? By the zero product property, I know I'm going to get x equals 0, and I could solve this one, and what would I get? If I set that equal to 0, what would the steps be to solve for x? I mean, I could factor it more if I wanted to, but I could also just, it's quadratic, right? And I can solve this quadratic equation. I can point to a single x, so I can just isolate x there, right? Going back to unit 2. So I could just add 1 and divide by 4. So if x squared equals 1/4, what does x equal? 1/2 or negative 1/2, plus or minus the square root of 1/4. That's just 1/2, right? So I get those pretty easily, but if I want the other solutions, that's kind of a mess, right? What can I do with that? I mean, it's a quadratic trinomial in packets of what? X squared. Right? I could think about this one as being 16x squared squared plus 4x squared plus 1, and that's what I'm setting equal to 0, right? That's not going to factor. We already know that when we use a difference or a sum of cubes pattern, we know that what we get for our quadratic factor is an irreducible quadratic. So I'm not going to be able to factor it any further, right? So I'm stuck with the quadratic formula. But if I try to do the quadratic formula, this is going to be pretty ugly, right? I'm going to get, instead of x equals, I'm going to get x squared equals negative b plus plus or minus the square root of b squared, that's 16, minus 4 times 16 times 1, so minus 64, all over, actually this is going to work out. This one happens to work out not too terrible, I guess. Isn't it? Yeah, it's not, I mean, it's not going to be great, but it's not going to be, yeah, it's going to be pretty hard, actually. Over 2a is 32. So if I simplify that, look what that becomes. Negative 4 plus or minus the square root of negative 48. What's that? What's the square root of negative 48?
4 square root.
4 square root of 3, I, right? Okay, but that's what x squared is equal to. So then you're gonna have to square root both of those. Well, how are you gonna square root it? We haven't talked about square rooting i's, right? So do you see this? We're running into some walls here. This really isn't a very good way to do it. You know, let's compare that to the other approach we took. If we think of this as being a difference of squares instead of a difference of cubes, see what happens. So if this is a difference of squares, that pattern's really simple. A squared minus b squared just factors into what?
A plus B.
Times a minus b, yeah. Okay, so then when we break this one down, we're gonna get x times, our a is our 8x cubed, our b is our 1, right? And so we're just gonna get 8x cubed minus, or plus 1 times 8x cubed minus 1. Now those are both things I can deal with. Both of those I can think of as being sums, one's a sum of cubes and one's a difference of cubes, right? How does this first one right here become a sum of cubes? What cubed is equal to 8 times x cubed? 2x. And then 1 cubed is 1, right? And then over here we're going to get 2x quantity cubed minus 1 cubed. Okay? So that works out pretty nicely then. These are each going to break apart. This is going to break apart into a plus b times a squared minus ab plus b, right? You see that? That's how this one breaks apart. And then this one's going to break apart into a minus b times a squared plus ab, 2x times 1, plus b squared. Right? That might look ugly, but it's not that bad. We can get all those zeros easily. Those factors are all quadratic or smaller. So we can easily find the solutions, right? Find the zeros. All the imaginary and real. So what are they? What are the solutions to this then? By the zero product property, x equals, what about that one? 0. Or x equals negative 1/2, x equals 1/2, and then I get some, these are going to give me imaginary parts, right? But I would just use the quadratic formula. I'm just going to get x equals negative b plus or minus the square root of b squared minus 4 times 4 times 1 all over 8. So if I simplify that, I'm going to get 1/4 plus or minus the square root of negative 12 is 2 radical 3. So 2 over 8 is 1/4. So that, there's a complex conjugate pair, right? And then I could do the same thing over here. What's the only thing that's going to change? Only thing that's gonna change is the A is the same and C is the same, but B is different, right? So I'm just gonna get x equals, my negative B becomes a negative 2 instead of a positive 2. But I'm still gonna get negative 12 in there, right? B squared minus 4AC. And I'm still gonna get 8 on the bottom. So I just get 8, or x equals negative 1/4 plus or minus square root of 3 over 4i, right? So I got all, how many should we have expected? At least 7, right? I have 7 total. We could get higher multiplicities, but we didn't. We got 7, didn't we? 1, 2, 3, 4, 5, 6, 7. 4 imaginaries, 2 pairs of complex conjugates, and then 3 reals, right? But they popped out pretty easily, whereas that was going to be pretty hard. Why? Hindsight's always 20/20. How could you have seen maybe that this was going to be a little harder approach than the other one? What's the rationale for in the future saying, oh, okay, let's do it the second one, not the first one? And remember, the big difference here was, in the harder way, we chose to break up this big binomial factor into a difference of cubes. In the easier way, we made a difference of squared.
Don't do a difference of cubes unless they are cubes. Quadratic polynomials.
Yeah, right. The difference of cubes give us harder factoring patterns, right? If we're doing packets of like x squareds or x cubes or some power of x in there, we're always going to have problems, because when you apply this difference or sum of cubes pattern, the quadratic part is going to be a problem, right? It's going to give you an irreducible quadratic. It's always going to give you i's, and you're going to have problems if you're setting some power of x equal to complex numbers with i's in them. That makes it a lot harder, right? It's a lot easier to do if we use the simpler of the 2 patterns first, which is the difference of squares patterns. Okay? Does that make sense? So those are pretty hard. I mean, I've never given those kinds of problems before, right? Not to make this for you guys, but it's kind of good to see that stuff. Think about that higher level of thinking about how are you going to strategically factor this thing, right? So you're not going to run into problems. Okay. I'll give you a few of those to work on. Just remember, you want to always, if given a choice, right? If you're taking a really, if you're taking some pattern that's going to be either some packets of powers of x squared or cubed, you always want to go with the easier pattern first, the difference of squares pattern. Okay. So what I want to show you today, I thought a new way of doing this. I think this is going to work really well. I'll show you just another little trick, and it's not even a trick that you already know it, but you just don't know that you know it. So let's go back for a second and let's look at how we would factor this simple quadratic trinomial. What would you do? You do magic numbers, right? You do magic numbers, and you'd kind of break this apart by knowing what the magic numbers are. Numbers that multiply to negative 40 and add to negative 6, right? So what are those?
4 and negative 10.
Negative 10, positive 4. Okay? So here's another way to look at that. If we know that the magic numbers we could take this thing and we're just going to split up that middle term into, instead of negative 6x, we're going to add it as a sum of two different coefficients of x. So negative 10x and positive 4x. And it really doesn't even matter what the order is. So we're going to say x squared, we're going to break up that 6x into a negative 10x plus 4x minus 40. Okay? Now that gives us, instead of a trinomial, that gives us 4 terms, right? When you get an even number of terms, and we're not going to go any beyond 4 terms, there's another way you can sometimes try to factor, and it's guaranteed to work in situations like this. If magic numbers exist, this technique will always work. It's called factoring by grouping. What you do when you factor by grouping is you're just going to split this thing into 2 groups of 2. So you're going to split it right down the middle. And then you're going to factor this in such a way that you're going to get you're gonna get a common factor between each of the two groups, right? So here's how we'll look at this. The first group, we wanna factor out the greatest common factor. What is that? X. Okay, so we're gonna break this up into the greatest common factor, which is X, times what we're gonna call, what I call the leftover. Whatever's left behind. What is that? Okay. Okay, on the other side, so over here, we want to end up getting the same leftover factor. So that has to be the same. Well, to accomplish that, what would we factor out? 4. Okay? So now look, how many terms do I have now? No. A term, the number of terms, the number of things that are being added. Got 2. I've got this big term plus that big term, right? So we want to try to factor out of each term a common factor. Well, what do we already know is going to be the common factor? X minus 10. Would you agree that each of these two terms has 2 factors? It has a monomial factor and then it has a binomial factor, right? The binomial factor is going to be the one that's the common factor. So if I undistribute or factor out the x minus 10, look what I get. I get x minus 10 times what's left behind. X, whoops, plus 4. Right? Isn't that how it factors? X minus 10 times x plus 4. Right? Okay. Now we could have done that, just to prove it to you, we could have broken it up differently. We could have broken it up instead into x squared plus 4x minus 10x minus 40 also. That's no problem. So what would the greatest common factor have been from the first group? X. What's the leftover? X plus, so what's the leftover have to be over here? If this is going to work, which means, what do I have to factor out? Okay, so then, you see that's going to work, don't you? Right, so now, we undistribute and x plus 4, and we're left with x plus negative 10, just x minus 10, right? Works either way. Yeah, that's pretty easy. I know you're probably thinking, well, why do we need it? I mean, that's so simple to factor. A quadratic trinomial when a equals 1, but this is actually kind of helpful if a is not equal to 1. Right? So we had to do, when we factored problems like this, we had to use bottoms up. I never really liked bottoms up that much because the process of going through it, unless you write down a whole bunch of stuff, you're actually doing some math that isn't right. I mean, it's a trick that always works, but we write some things down when we do bottoms up that aren't mathematically correct. Okay, but we don't have to. We could also just do it the way, I'm not suggesting you shouldn't use bottoms up. It works. And it's simple. What would the magic numbers have to multiply to here?
60.
Yeah. What would they have to add to? So what numbers do that? Negative 20 and negative 3, okay? So we can do the same thing. We can break this up into 15x squared, and you told me the magic numbers are negative 20 and negative 3. So we could do 15x squared minus 20x minus 3x plus 4. Okay, what's my greatest common factor from group 1? 5x. What's left behind? Now you know if you can find magic numbers, it's guaranteed to work. So you know that you're going to get back a 3x minus 4, but what do you have to factor out to make that happen? Okay, so then how does it factor? Okay, if we want to, we could have gone 15x squared minus 3x minus 20x plus 4. We would have factored out that this time, what, a 3x? Leaving behind 5x minus 1. Over there we need a 5x minus 1. So that means we have to factor out, what, a negative 4? Well, is that just going to give us that? Okay. So, it works for quadratic trinomials, but we can also use this for situations where we are stuck at the beginning with 4 terms, right? Now, does it always work? No, it doesn't. It's only going to work if you can get that first pattern to work out. If you can factor out a greatest common factor from the first group, and if you end up getting the common leftover factor. If you don't, it doesn't work. Okay? But sometimes it does. So what about one like this? You're going to break this into 2 groups, right? Same pattern. 8x to the 4th plus 72x cubed plus group 2 x plus 9. Okay, so great thing. But what do we, looking at both terms, what do we probably need to have for our leftover group from group 1?
X plus 9.
X plus 9.
8x.
And to get that, we could factor out x cubed okay, well, what do we factor out to get that?
1.
Nothing, just a 1, right? So it breaks up into what then? And I guess I did it back. We should have probably done the x plus 9 first. It doesn't matter. If we factor out an x plus 9, we're left behind with 8x cubed plus 1. Okay, so are we done? It says completely factor the polynomial.
Sure. I felt right. We still got the x cubed in
Okay, that one's done. It's linear, right? This one is I mean, maybe not, but could we go further?
there.
Yeah, we could. So what pattern would that fit? What's the only one it could possibly fit? Sum of cubes, like an a cubed plus b cubed. So if it's going to fit that pattern, this guy right here would have to look like something cubed plus something cubed. Well, that's a 1. What would the first packet be? And then we just follow our pattern, right? A cubed plus b cubed is just a plus b times a squared minus ab plus b squared. Can we go further? That's quadratic, but we know it's an irreducible quadratic, right? Because it's part of the difference of cubes pattern. We know we can never go any further. Okay, we're done. Try another one. Try that one. I'll give you a hint. There's something we haven't needed to do yet, that we always want to try to do first. Pretty good hint. Just to make sure people don't start off on the wrong path here, what do we have to do first? Well, we can't change it because it's not an equation. It's an expression. We're just trying to factor an expression. What do you think?
Pull out a negative 3x squared.
Good. Pull out a negative 3x squared. So we always, when we factor out a greatest common factor, remember it always inherits the sign of the leading coefficient. So if that's negative, we want to pull out a negative greatest common factor. So we end up with a nice positive leading coefficient. Okay, so first step. Now I'll let you take it from there. First step, we're going to pull out a negative 3x squared, which leaves us with what? X cubed minus
6x squared.
6x squared, good. What? Plus 25x, good. Okay. Now, how many factors do we have there? No? Two. Got an orange factor and a white factor, right? Because the factors are things that are being multiplied together. The orange factor we're done with, right? Can't go any further with that one. But the white factor we can go further with. How many terms are there in the white factor? 4. So our only approach is factoring by grouping, which is what this is called, we're talking about, right? We can't do any of our other tricks because they all apply to binomials and trinomials. So this new strategy we're talking about is what we can try if we've got a 4-term factor we want to break it down. Okay, so try that. Take a minute or two and try that. Okay, what do you think? For the second factor, so one thing I like to do is I like to kind of nest grouping symbols so you can keep track of what layer you're on. So I'm going to make this, I'm going to put these all inside script brackets. And then we've got our line down the middle, right? So group number 1, what's going to be my greatest common factor? X squared. What's left behind? So what do we need over here? And what would I have to factor out to get that? Or does it work? So here's kind of the way I would do this one then. You know that here's the order of of events, right? So you know that you're gonna factor out what the greatest common factor is, you're gonna find out what's left behind. You know that's what has to go there, right? Well, the only way that could work, I know I need a 25x, right? So for sure, I know that that's gonna have to be a 25, but to check it, I would just distribute and see if it works. That's gonna give me 25x minus 150, so it all checks out, right? So then, where are we now? So I've got my negative 3x squared out front. What can I factor out of each of those two factors? Okay, what's left behind if I do that? Okay, can I go any further? So that one's quadratic, but it's done. It's a monomial, right? That one's linear, so it's done. That one's quadratic. Can I use a pattern to split that up? What would it be? Can I? How come? Because it's sum of squares, and there's no pattern for sum of squares. Right? We only get difference of squares, there's a pattern. But sum of squares, there is no pattern. That's the tricky one. So that's our answer. Okay, so what if they give you a different kind of a problem here? So this one, and you're going to get both of these kinds of problems on your assignment. So one of them says completely factor. So on the completely factor ones, we had to break these things down further, right? And we didn't have a choice. We just had to. But this just says find all complex solutions, right? So the only difference is that when we're solving this thing, we can bail off the factor train whenever we want to, right? As soon as we get down to quadratic factors or smaller, I can find the zeros of those without factoring if I choose to. Right? That's really the only difference. Let's see if let's do one more. Is that a good one? Or let's do that one. That one looks a little hard. Okay, so what am I going to do first?
Move it all, get everything to one side.
Okay, move it all to
The left.
the left. That doesn't matter. I mean, we could move it to the left. If I move it, I mean, really, I'd probably move it right, just so you have positive number of x to the fifths. So if I move everything to the right, what am I going to end up with? How many x to the fifths?
24.
How many x to the fourths? Well, 40, I guess, right? How many x cubes? None, they go away. Okay. How many x squareds? How many x's? 35, okay? So there we got 4 terms. So we could try to factor this one by grouping, right? So we'll just break this up into first group. What's my greatest common factor in the first group? Or is there anything I can divide both sides by? I guess we should look and see. No, and I can't factor anything out, right? No variables. That one doesn't have an x. So I guess we're stuck with that. What's our GCF for the first group? 8x maybe? But 8x to what? 8x to the 4th. So I leave behind what?
3x.
Okay. Plus, we know we've got to have the same leftover if it's going to work. Okay, well, 3x times what is 81x squared? Okay. Hold it, something's wrong. I didn't put an x there, did I? Oh, you know what, we could, okay, I messed this up. I forgot to put the x there. So what could we have done in the original problem? Could have factored out an x, right? So let's do that. If I factor an x out of this whole thing, what's that gonna do?
It knocks all of the exponents down
Yeah, it just knocks all the exponents down by one. So that's a 4, that's a 3, that's a 1. That's gone. Oops. 4, 3, and that changes then. We're factoring out an 8x cubed instead, right? And so over here, I 3x times what is 81x? 27. And so now we'll just check to see if that works. So if I distribute the 27, I'm going to get 81x, and then 27 times 5 is 135. So it works, doesn't it? Right? So then this is equal to, we've got our x out front. We can factor out, I guess I need to put that too, don't I? We have our x out front. We can factor out of each group of 3x plus 5. And then we're left behind with 8x cubed plus 27 equals 0. Okay? So now, here's another place where you could potentially take a little shortcut. If this question said, and I'm going to give you some that eventually like this that do, where they say just find all real solutions. Okay, if I just want the real solutions, all I'd have to do is just isolate that x. And we'll talk more about that kind of later. But right, I wouldn't have to, the only reason that you might remember us talking about this before break, the only reason I'd really have to use this pattern is if I want to get the complex solutions that come out of that quadratic, irreducible quadratic factor. I'm asking you for all complex solutions. So we have to factor that again, right? We can't bail off the factoring train yet because it's not quadratic, it's cubic. So I'd have to break it down further. But if I was just looking for real solutions, I could take a little shortcut here, right? I could set that factor equal to 0. And what would the steps be to isolate x there? Subtract 27, divide by 8, so I'd get x cubed equals negative 27/8, and then what? We haven't really talked about doing this yet, but you've probably done this before. Cube root both sides. So I would just get x equals negative 3/2. We haven't talked about this, but when you take an odd root of something, you don't get a plus or minus, you just get one answer. And that's kind of like next unit. We'll get there. Okay? All right, but we need to get both of them, so we would have to break this one down a little further. That's a sum of cubes, right? That's the same thing as saying 2x cubed plus 3 cubed. So how's the red factor going to break down? There's my A.
2x plus 3.
I got 2x squared. Well, what is 2x quantity squared?
4x squared
Minus. Right, we got to follow our pattern. Yeah, 2x, A is 2x, B is 3. So A times B, 2x times 3 would be 6x plus B squared. Right, and now we can just set everything equal to 0 and solve, right? That make sense? Yeah, we find all the zeros. Okay, that's a lot of stuff, all right? I'm gonna give you a work day tomorrow, kind of work away on this stuff and get questions answered. All right.